Hello, my name is Wyatt. I'm going to be going over the blood, its composition, how we regulate it, and hemostasis today. So let me just get into it. First, we'll start with the composition of the blood. I don't know why it's doing that. Try unplugging that. There we go. Okay, that fixed it. So the composition of the blood, um, there are two or three main types of things. The first, there's 55% of the blood is our plasma. Okay, and then 44%, 44-ish percent is our red blood cells, and then less than 1% is going to be our white blood cells and platelets. Um, with the plasma, 92% of the plasma is going to just be water. 8%, not 80, 8% is going to be colloids, which are just proteins in the blood. There's a couple different ones. One example is albumin, another is globulin, and another is fibrinogen, which we will be talking about today. As far as red blood cells go, that's the whole 44%. And then, so this is going to be our composition of blood. So if we look at blood in a tube here, um, down here, we're going to have our red blood cells. Up here, the top will have our plasma. And then that middle layer is going to be our white, buffy layer, which is going to have our white blood cells and platelets right there. So that's the composition of the blood. And something interesting with the blood is we're constantly making millions of red blood cells every second, every minute. Um, so constantly putting a bunch of red blood cells into the system, and obviously we're not constantly increasing how much blood we have, so some has to be removed. So the next thing we're going to talk about is the red blood cell removal. So if we draw out kind of an abstract red blood cell, it's got this kind of interesting shape. And this is so that maximum amount of oxygen can bind to its hemoglobin and so that the blood can carry a good amount of oxygen. But after about 120 days, it's going to lose its shape, become circular, and begin to kind of break down, begin to not be as useful. And when that happens, it will be identified and taken to a couple different places. It could be the spleen, for example. It could be the bone marrow. It could be a number of places. Let's just say the spleen for here. And it's going to be broken down into a couple different things. So broken down. There's two different things, main things that the cell will be broken into. Um, it'll be broken into a bunch of different pieces and into platelets and such. But as far as its hemoglobin go, which is what we are most interested about, it's going to be broken into heme and globin. Now, our globin is just going to become amino acids that will be reused in the body. The heme, though, that's where it gets a little more interesting. The heme is kind of a circular structure with an iron in the middle. So immediately that iron is going to be lost. And the iron's going to go back to the bone marrow to be reused as new red blood cells are made. So the iron will go back. And when that happens, the heme will turn into something called biliverdin. Biliverdin, I remember it as green. It can also be blue. That's kind of why you get the blue-green look with bruises at first. And I remember that because biliverdin has verd in it, which means green in Spanish, verde. So this is going to be blue/green. The biliverdin is then going to be turned into something called bilirubin, which is yellow. The bilirubin is going to go to the liver. So we'll just say liver. And once in the liver, it's going to be conjugated. So it's going to become conjugated bilirubin. And basically what that means is it'll become polar. Once it's become bilirubin, the liver is going to combine it into the bile. So it goes to the bile. The bile is going to go to the intestine. And in the intestine, bacteria are going to come in and eat everything around the bilirubin. And they're going to turn the bilirubin into something called urobilinogen. That urobilinogen can either end up in our urine or in our poop. It's about 50-50. If the urobilinogen stays in the intestines, it'll eventually be pooped out. It'll have a brown color and it will be converted, let's get a brown, into something called sterobilin. But the urobilinogen can also be retaken up by the blood. So kind of goes into the blood, goes to the kidneys, and then it'll be put back in it'll be peed out and it'll be turned in to urobilin, which is what makes your pee look yellow. So that's how our red blood cells are removed after they die. So they have a bunch of different uses, but we have to get rid of that biliverdin because it is harmful, and if we're not able to get rid of it, that can be a problem. So next, let's talk about hemostasis. Uh, hemostasis is how we stop bleeding, basically, how we terminate bleeding. And it's got 3 different steps or things that happen. We've got the vascular spasm. We have the development of the platelet plug, sorry. And then last, we're going to have the coagulation cascade. I gotta make sure I spell that right. Cascade. So basically, what's going to happen here is, uh, say we have our basement membrane here. It's collagen mostly, and then we have a blood vessel, the wall of a blood vessel. We've got these endothelial cells, and a cut happens. So there's a cut in this blood vessel. The first thing that's going to happen is something called a vascular spasm. So the pain is going to cause the damaged blood vessels to vasoconstrict for a short amount of time. So initially, there's going to be a shortage of blood to this blood vessel. Unfortunately, it doesn't last for very long, and eventually the smooth muscle will relax, and will start bleeding more. So that's when the platelet plug comes into play. So let's break it down. So these endothelial cells, they're releasing, when they sense this cut, they're going to be releasing, or I think they're constantly releasing VWF. The VWF likes to bond to collagen. So it's going to be floating around. It's going to get pulled out here, and it's going to bind to that collagen. It'll bind to that collagen. Now what happens is, when we broke down our red blood cells before, some of them become little pieces called platelets. We have a bunch of these in the blood. And the platelets actually have a receptor for VWF. So the platelets floating along, and then it comes up and binds to that VWF. So let's draw that. And what's going to happen is, there's a stretch receptor on that VWF receptor. So when it binds to VWF, it's getting pulled towards the collagen. That's going to open, and calcium will enter the cell, which is going to cause it to change conformation. So it's going to get much bigger. Now, that's great and everything, but how do we get this platelet plug? Because this is just one. So what happens is, the platelet, only one platelet right now is activated, but obviously there's going to be many more platelets in the blood. To activate them, there's a couple different things. So there's this thing called fibrinogen that's turned into fibrin. When fibrin is released, it's going to activate these cells. So let me just see here. Okay, so I forgot a step. So inside this cell, we have these things called granules. So I'll just make a chart over here. We have dense granules and we have alpha granules. The dense granules are going to release ADP and calcium. Why does that matter? Because these platelets that are floating along here, if ADP comes along, it's going to activate them. And it's going to cause them to get bigger like the other one. There's another thing that this activated platelet is releasing, and we'll just use different color. And it is called TXA2. It's going to be releasing that. The TXA2 is going to come here. That will also activate platelets. So now we've got our platelets activated. So how do they stick to each other? That's what I was talking about before with our fibrin. So all of these cells, now these platelets are going to be activated. So they're all big. They all have a bunch of fibrinogen or fibrin receptors. So fibrinogen is going to come along here in the blood, and it's going to bind to our activated platelet, and then it's going to bind to another activated platelet. So if we erase that, we draw. They're both binded to that fibrin, so they're going to be connected. And if we draw another one, that fibrinogen is connecting them, and this is what we call the platelet plug. So this platelet plug is what's going to block and stop bleeding for now, and eventually it's going to heal our blood vessel. Once the platelets are linked together, that is when our third step, the coagulation cascade is going to begin. So let's draw that same thing just down here. So we're going to have something called factor 12. Factor 12, when the collagen is exposed, it's going to turn into 12A, which is going to be able to turn 11 into 11A, which is going to be able to turn 9 into 9A, and with the help of factor 8, is going to be able to activate factor 10A. And that'll lead us to our common pathway. So with factor 10A and factor 5, factor 2 will be turned into 2A. This is something called thrombin. And thrombin is going to be able to turn fibrinogen, which is inactivated fibrin, into fibrin. So what color did I use for fibrin? So fibrin is right here. Fibrinogen is over here. So basically, the fibrin is going to be produced, and that is what's going to allow our cascade, our plug of platelets to happen. So we have to get to that common pathway. This is what we call the intrinsic pathway to get to that common pathway. This is intrinsic pathway. And then below it is our common pathway. I should probably use a different color for that. We'll say yellow. So our common pathway. And then there's another pathway that we can take that's not going to work as fast, but this is going to happen. It's called the extrinsic pathway. And this is when we have some tissue damage. So say we have some tissue cells here. These are exposed, they're damaged. What's going to happen is that is going to allow for, That is going to allow for something called factor 7 to turn into factor 7a. Factor 7a is also able to turn factor 10 into factor 10a and continue with our normal common pathway. This is called the the extrinsic pathway. So these are the different pathways we have to being able to stop a clot. The intrinsic pathway is going to work much faster because one factor 11 or factor 12 cell can trigger many factor 11 cells, which can trigger many factor 9 and factor 10. So that's going to cause a much greater kind of ripple effect than just the factor 7 converting factor 10 to 10A. So intrinsic pathway is going to be more effective, but we need both. Upon the clot formation, clot retraction is also going to occur. So what happens with the blood clot breakdown is we're going to redraw our clot here. So we have our BWF, our platelets, and our fibrinogen. And then we have more activated platelets. What's going to happen is retraction is going to occur. So calcium is going to enter the cells and they're going to begin to contract because these platelet cells actually do have actin and myosin in them. And so they're going to get more condensed. They're going to get closer together. And they're going to begin to pull the walls of the blood vessel together and start to seal up that hole. So that's how it works. And then eventually what's going to happen is something called plasmin is going to come in and it's going to attack that fibrin, break it down. So we'll give some arrows here, some arrows there, and we're just going to be left with that one platelet right there that will eventually be pulled up to the top. But our connections with the other platelets will be gone. And they'll just go away. And our fibrin has just been broken up by the plasmin. Plasmin is made from plasminogen, or plasminogen, by something called TPA. TPA is going to be produced from epithelial cells in the presence of fibrin. So, in presence of fibrin, or I'll just say epithelial cells plus fibrin is going to turn on TPA. TPA is going to take plasminogen, which is just inactivated plasmin, and it's going to activate it, turning it to plasmin. So fibrin, the minute that it's exposed to the epithelial cells, is going to begin its own breakdown by activating TPA, and TPA is activating plasmin. So plasmin is going to come back here and destroy fibrin. And that is the process of our coagulation cascade and how the clots are actually broken down. And that is about it for the blood. Thank you so much for listening and have a great night.